Once again, Spin Launch are keeping their cards close to their chests on this one, but they did give me a demonstration of the door closing in their factory and engineering hub in Long Beach, California.
Well, it's moving really fast, and so when the without specifying, you can do a countdown.
Yep. So whenever you're ready for a countdown, just let me know.
Yeah. So basically, what's going to happen is, this is going to be filled with a, for lack of a better word, like a black door, which basically you'll see that you can pass through this with a vehicle, and then in an instant, it's going to be closed.
Okay.
So, and again, it's like faster than the blink of an eye. So you'll see a little bit of settling after it closes, but it's, basically 95% closed within, 30 milliseconds.
Oh, wow. Okay.
Closing airlock in 5, 4, 3, 2, 1.
It's pretty fast.
Yeah, that's not what I was expecting.
Yeah, it's fast.
So it actually closes, like it's actually hinged.
There's a pivot, yeah.
Okay. Yeah, I wasn't sure if it was going to be a sliding thing, but the hinged one makes sense as well. Yeah, that wasn't what I was expecting.
So that's 100% reusable. Basically, you can set that back up again and do it again and again and again. So
Right.
that's a key aspect of it, is that you don't have any major consumables in the process. So
That's cool.
yeah, it's fast. Visceral.
All right.
I don't know.
It's a door closing. I don't know what to ask.
It's really important not to let air back in. So
Yeah.
that's why I have it.
Oh, everybody jumps.
So the airlock is a really critical subsystem of the overall architecture. As you travel from vacuum into the atmosphere, because the tether is still rotating at high velocities, you want to maintain the vacuum inside of the vacuum chamber. And so the airlock is your first line of defense for that. And so we have multiple redundant airlocks, just like what you see here, that the vehicle passes through and it subsequently closes behind the vehicle, preventing the air from inrushing and re-entering into the vacuum chamber. So the exit tunnel is really the only portion of the chamber that experiences a rise in pressure.
I imagine that allows you to reset and increase frequency of launches as well if you're not having to reestablish.
Yeah, totally.
the vacuum.
So you can do you can essentially provide an airlocked space for the end of the tether as well, and so you can basically just repressurize that space as you load in new vehicles. It's possible you could do vehicle integration in vacuum, but currently we're anticipating actually repressuring a small portion of interfacing around the tether, repressurizing a small portion and integrating the vehicle without it being in vacuum.
How many launches a day do you think you can manage? I think that's one of the advantages of this, that you can.
Yeah, I think on the very high end, it's upwards of 10. I think on the low end, it's about 5 is a pretty good nominal target for us. We see viability there.
In Spin Launch's public videos, the secondary airlock has simply been sheets of mylar. This is one of the few problems that becomes easier as the launcher scales. As the exit tunnel grows in length, it will take air longer to reach the door at the base of the exit tunnel. Spin Launch have only just begun these 1/3 scale tests, with their fastest launch to date at 1.6 Mach, slowly ramping up the speed of launch as they test their systems. This prototype launcher features some other simplifications compared to their final planned configuration. One of the most obvious problems to tackle is the issue of vibration. When a spinning object's weight is not evenly distributed, it will vibrate. This is how rumble feedback works in gaming controllers, a simple electric motor with an uneven weight attached. However, with a structure as large as Spin Launch's tether, spinning several times per second, any imbalance could shake the entire structure to the ground. This is a major problem, because, by design, the tether releases a 10-ton weight right at its maximum velocity. Spin Launch needs a way to balance the tether after launch. There is a very simple solution to this problem though. Release a balanced weight from the other side of the arm at the same time. Right now, they are simply releasing a counterweight that slams into an armored section of the vacuum chamber. We saw one of these counterweights being manufactured out of fiberglass in the Long Beach factory. However, over the long term, having to clean up the mess this creates after each and every launch is far from ideal. The ideal solution would be to release a counterweight in the form of another launch vehicle after a single half rotation of the tether. The oil-filled journal bearing the massive axle sits upon should be able to absorb the force of this imbalance over a period of time this short. The next issue we need to concern ourselves with is the aeroshell punching into the atmosphere at Mach 6. This, again, is a fairly unique problem. Typically, weight is a restraining factor in aerospace, but for spin launch, the energy required to spin the aeroshell up to speed is actually rather trivial.
It's on the order, I like to use the analogy of like a Tesla, right? So the Tesla Model S Plaid is about 0.7 megawatts. So on the low end, it's about 100 Teslas, but it really comes down.
Is that for the full scale?
Yeah, for the full scale, yeah. For the orbital system, you're talking about like on the low end, on the very low end, it's probably about 65 to 70 megawatts. And again, that really depends on where you end up with the final orbital tether, whether or not what safety factor you operate with, what tether strength you end up with, your effective, tether, cross-sectional strength. That all feeds back into itself, and then you have to, kind of scale it accordingly. I would say, like, really conservatively, like, if you wanted to spin up really fast, then you're talking about a higher power demand. So whether you want to spin up in an hour or 2 hours, proportionally makes a difference of how much power that you need. But on the high end, you're talking about maybe 150 megawatts of power, which is like, I don't know, maybe in layman terms it sounds significant, but you can. There's motor catalogs where you purchase, the motor that has that capacity, right? And so this is, it's industrial scale hardware, and certainly, mostly off the shelf.
Do you need to worry about like grid integration at all when you're suddenly drawing that much power?
No, I mean, for better for worse, no, because you're typically, particularly for early. Orbital accelerators that we're building, we're expecting them to be in really remote locations, kind of remote coastal locations, greenfield sites that don't have substantial existing on-site, resources or power. So you're basically, bringing your own power, and so you have to, decide on, what is your energy source? Are you doing energy recapture, et cetera?